16, VariChill.
Alrighty, so I spent the last 2 summers working on health and sanitation trips in Western Guatemala, and something that became immediately apparent in our time there through visiting local clinics and independent research was the fact that preventable diseases were impacting our partner community very, very strongly. So one of the main issues that the partner community faced was limited access to grid power. Vaccine storage is incredibly temperature dependent. You need to effectively maintain them in a particular temperature range in order for them to remain effective. So our team sought out to mitigate this problem and confront it. So I'm Leandro, this is John, Julian, and Dane, and we're VariChill. So our goal was to design a solar-powered high-efficiency refrigerator for vaccine storage in developing nations. As I mentioned, we had a few specs established by World Health Organization benchmarks. Temperature range was one of them. Additionally, we wanted ample storage space so that we could effectively store a lot of vaccines. Battery life was a really important issue because if we lost access to grid power, we needed to effectively maintain our system. And additionally, we wanted to optimize it so that it's operating on the least amount of power possible.
So what makes our project unique is the way we chose to cool the system. Most fridges for solar-powered vaccine fridges are powered with compressors, which are extremely hard to maintain and very expensive, so we went a different route. We settled on a thermoelectric cooler, which is a solid-state cooling device. When DC power is applied, one side gets very, very hot and one side gets very, very cold. And so with proper heat dissipation and air circulation, as you can see in the graph, we can use this system to effectively cool a space. So with this in mind, we designed our overall system. On the left, you can see the power system. On the left, you can see the power system with the solar panel and everything. On the right, you can see the control system with the photon wireless microcontroller at its heart, controlling the system's cooling functions, circulation, and monitoring the fridge's temperature and other system alerts. This is not working. And so one of the issues with the Peltier units, or the thermoelectric coolers, is that they must always remain on to maintain temperature, low temperatures in the fridge, and the second that they turn off, they basically become a heat pump, pulling heat into the space they're storing. So to address this problem, we devised a 2-chamber system. The top chamber is a cooling chamber with a thermoelectric unit, and the bottom chamber stores the vaccines, and these chambers are linked with a sealable hole. When we're cooling the fridge, the thermoelectric unit is on, and air circulating throughout both chambers, cooling the space down to the 41 degrees that we need. And when we're ready to turn off the thermoelectric unit and conserve power to expand the battery life, we deploy the plug into the sealable hole via a servo-powered racket pinion mechanism, which seals the bottom chamber and extends the battery life by keeping it cool.
So we're an interdisciplinary team, so the way we decided to break up the work was based on our specialties. So John's an electrical engineer, so he focused mainly on the power and the solar integration. Dane's a computer engineer, so he did everything with the embedded system and microcontroller programming. And then me and Leandro are both mechanical engineers, so we focused a lot on the fabrication. Leandro specialized on the thermodynamic analysis and installation, whereas I did a lot of the CAD modeling and mechanical design. So here you can see a comprehensive CAD model of our fridge. This is a cross-sectional view from the side. On the left is the front, and on the right is the back. Just to highlight a few key components, in the top we have the embedded system, the rack and pinion, and the thermoelectric element. And then as you shift down to the vaccine chamber, you can see thermal battery storage, and then space for the vaccine storage. Additionally, around the exterior, you can see the insulation, which is 2-stage, consisting of expanded polystyrene and melamine. And then here you can see a 3D version of that same CAD model, and pass off to Dane.
Great. So for this system, we implemented an online monitoring dashboard. So you can see real-time updates of the temperatures, and most importantly, the historical data, because maintaining these temperatures and knowing the temperatures at every step of the way is really critical to know if these vaccines are effective. So you can see, basically, it's cooling on, is the plug open, and then there's also a sister website to this for admins, so they can actuate both the cooling and the plug system. And so here is a video demonstration of our system. So here's a 3D CAD model, and then right here is the actually implemented system that we were able to achieve. This is the embedded system, which controls the power and all of the temperature monitoring. And here's the back with the element and the power. Here's a vent that connects the top to the bottom. here is a demonstration of our rack and pinion system going up and then going down to seal the chambers. And here is an example of when we reach the optimal temperature range, we get this really satisfying blue light that shows that we're actually nice and chill. And so here is the total cost of our product, or not our implementation. So $784, it's particularly interesting to note that the thermoelectric cooler is only $10. And when you compare that to compressor methods, which can cost north of $300, we greatly reduce the cost for our whole system. And so here is testing for both a single chamber and a dual chamber configuration. And both of the dark blue lines are the temperature within the vaccine chamber. On the left with a single chamber, it shows that when we turn off power to our system, we cut the cooling, it exits the optimal temperature range within about a minute. And when we implement our dual chamber system, we're able to maintain that temperature for a lot longer. And recent tests actually show that we can maintain that temperature range for about an hour. And so here's our duty cycle. So we were able to achieve a duty cycle of about 60% to increase the longevity of the battery life. And so really simplistic view, we show that when you turn the temperature or the cooling element on, the temperature within the top chamber increases as the heat comes in, but then we're able to recool it and maintain the temperature in the bottom chamber, which is the most critical component.
So with regards to power, we were able to achieve a power point of 65 watts with the thermoelectric unit consuming the lion's share of that power. The embedded system and the other circulation fans only account for roughly 15% of that. When you look at the power point, compared to industry leader of DC compressors, you can see in the highlighted blue box that at that desired temperature range, our fridge is in that power range, if not less.
So again, to reiterate, these are the specifications that we set out at the beginning of the year. We successfully achieved our temperature, our desired temperature. Additionally, our storage spaces of 10 liters were effectively cooling that space. Our duty cycle effectively extended our battery life 1.6 times, and our system was summed up in a nice 65 watts.
So here you can see the actualization of those goals. We have the three major components: the solar panel, the battery, and the fridge. We're Team VariChill, and we want to thank you very much for your time.